Hi, I'm Morgan, and I'm from the Missouri S&T rocket design team.
And I'm Tommy from the S&T Multirotor design team.
We built a rocket to drop a quadcopter.
And we built the quadcopter being dropped out of the rocket.
Together, for the first time in our university's history, two design teams are coming together for the same competition.
Both teams have worked hard to prepare for the Argonia Cup. We've engineered an excellent solution to this challenge, and we're excited to show what we've come up with.
This is the general flight path the rocket will take. It starts at launch. Once the pad is clear and the keys are turned, the solid motor ignites and the rocket shoots off. The motor only burns for 2.3 seconds, and the rocket coasts until it reaches its apogee at 9,600 feet. Once our electronics detect that the rocket is at apogee, a CO2 charge will split the rocket at the lower coupler. After a slight delay, both halves will deploy their smaller drogue parachutes. At 1,500 feet, the quadcopter is dropped and the main parachutes are deployed. While the quadcopter is flying to the target, the rocket parts safely fall to the ground under their main parachutes. All that's left is for the quadcopter to land on the target.
We're using OpenRocket's flight simulator to project our apogee. With our current design, it reaches a peak acceleration of 20 Gs and shoots 1,600 feet above our 8,000 foot requirement. This should be more than enough wiggle room to account for any error in our calculation. This is a model of the completed rocket. At 9.6 feet tall and 35 pounds, it's built from a fiberglass frame and projected to fly to a height of 9,600 feet. The rocket uses a dual deploy recovery system, with a twist. Rather than splitting into 3 sections, it splits into 4. And rather than staying connected as one system while undershoot, the rocket is disconnected in the middle, and both the top and bottom sets have their own dual deploy systems. The rocket flies on an Aerotech L2200 motor, chosen for its high impulse at 1147 pound-seconds. It only burns for 2.3 seconds, but at a mighty 700 pound peak thrust, we are able to ensure an apogee well beyond our 8,000 foot requirement. The lower coupler houses one of the electronics bays, as well as the black powder charge wells used for separation and parachute deployment. Note that the upper charge wells are CO2 charges, chosen to prevent damage and corrosion to the quadcopter, which is housed in the above section. This is similar to a typical dual deploy system. The upper charges deploy at apogee to release the smaller drogue parachute, and the lower charges activate at a lower altitude to deploy the larger main parachute. The upper body tube houses both the upper electronics bay and the quadcopter. The upper electronics bay is very similar to the lower electronics bay, although it also includes a solenoid control system. There are only charge wells on the top of this electronics bay, since the coupler only needs to separate from the nose cone above. The quadcopter is held in by a spring release system, pinned together by a solenoid. Since the upper body tube is under drogue at the time of this quadcopter's release, the bottom of the tube is open to empty air. When the altimeter in the upper electronics bay reaches the desired altitude, the pin is retracted and the quadcopter is released. The nose cone is an ogive shape with an aluminum tip. Both upper stage parachutes are housed here, which means both will have to deploy at the same time. Since the purpose of a dual deploy system is to deploy the drogue parachute first, the larger main parachute will be held together by a Jolly Logic chute release until the desired altitude is detected. All of these elements come together to make the one united rocket. One rocket on the launch pad, 2 rockets on the ground, and 1 quadcopter on the target.
The biggest challenge for our team is how much technology we have to pack into such a tight space. The restricted diameter of the rocket, long flight distance, and extreme conditions require our aircraft to be lightweight, compact, and durable. This is the Kraken. To meet with the constraints, we designed a carbon fiber and aluminum frame with folding arm mechanisms, vertical electronics placement, and highly efficient motor combination with folding propellers. This allows us to fit a 7-inch multi-rotor frame into a 5-inch rocket. The extension springs will pop the arms into place and make sure the aircraft is ready to fly immediately after ejection. The Kraken will likely be in a high-speed tumble, but the self-correcting nature of quadcopters and the manual thrust will help stabilize its descent. Once stabilized, a pilot on a remote link will take control of the aircraft via radio and safely maneuver the aircraft away from the falling rocket. The Kraken will then return to the target landing area autonomously. However, an FPV system is available for the pilot if necessary.
The aircraft is powered by a single lithium-ion battery, RTK-assisted GPS, Pixhawk Cube flight controller, and 4-in-1 ESC. This combination gives us approximately 8 to 12 minutes of flight time, a 4-to-1 thrust-to-weight ratio, and an operating range of about 5 kilometers.
We're confident in our designs and will continue to refine them until competition.
We're excited to see everyone there.